Okay, let's start. By the way, sorry for announcing the group late. So this is our group. So every day, maybe after next week, we're going to have a fixed group. But before then, we're gonna switch group every day. So yeah, that's why you're sitting on the back. So okay, so are you sitting in the according to the group? Are you guys sitting according to the group? Okay. So maybe, yeah, so one's there, yeah. So the reason why I'm trying to, this is a random group. So the reason why I'm giving you the random group is I want you to get to know each other, as many people as possible before fixing the group. So we're going to have, so raise your hand. I heard one person is first time being here. Raise your hand if you're first time. Anyone else? So what's your name? Are you in the, is your name here? No? What's your name? Okay, so you're in group 6. Group 6 is somewhere there. So you don't have to sit next. You can sit in front. You can sit in front of 6. So here is our syllabus. I mean, not the syllabus. It's our course website. So if you're not registered, you might want to take a photo of this QR. So every class material will goes to this Notion site. I uploaded the link to the LMS. And did you take the QR? Shiwan, did you take QR? Okay. And there's lecture videos here and lecture slides here. I uploaded my handwriting last time here. And today's materials here, groups are here. Okay, I didn't give you a chance to discuss within your group last time, so we're gonna have lots of discussion instead. Okay, so is there anything you want to ask before we start? No? Okay, let's see. Okay. So we're going to see lots of matrix and cat notations. So it's about quantum gate, but let's begin with our matrix. So for some of us who are familiar with mathematical theory, it's quite easy, but I'm not assuming everyone is comfortable with mathematics. So I'm giving you the most basic concepts from. So matrix is just a two-dimensional array of numbers written in this form. The important thing is you may familiar with the matrix of real numbers, but every time we mention a matrix in quantum computing, it's a complex matrix. Okay, so even if you see the real numbers every places, you have to consider it's a real number in the complex number. So this is how you add two matrices, basically. You basically add element-wise addition, and this is how you take a scalar multiplication. You take a scalar multiple on every component. And here is how you take a matrix multiplications. And the important thing is the matrix multiplication is not commutable. So if you change the order of multiplication, you get different matrix multiplication. So it's quite closely related to how you act a quantum gate on a quantum state. So each matrix, we're going to explain this detail later. Each matrix will represent a quantum gate. And so matrix multiplication, the fact that matrix multiplication is not commutable means that it depends on which order you apply quantum gate, your outcome. So your outcome is. So here you will see that these two matrices are same on the right, but the results are different. Okay, so here is one more concept that you might not familiar with. I explained last time, although it's a tensor product, and there are many places where concept of tensor product appears. For example, if you learn algebra, there is a tensor product. There's a tensor product or tensor in geometry. Here is a tensor too. There are they are all similar in abstract sense, but here is most basic concepts of tensor. It's just matrix multiplication, and elementary wise, it's a kind of a stupid way. So you see, if you take the multiplication of two matrices, like this one and this one, this is something like elementary school student might think of it as a matrix multiplication. You just multiply each element to every element in here as if it's a component of this matrix and so on, like this one. So at the end, you get bigger size than the previous size of the matrices. So here you multiply 2 by 2 matrices to get 4 by 4 matrices. And another concept is the conjugate transpose of a matrix. It's basically you take the transpose and take conjugate on each component of the matrix. As I said, all the components are complex numbers, so conjugate is a different complex number. And this is a technical term that we're going to use later. A square matrix is called Hermitian if its conjugate transpose is same as original matrix. And here are another technical term, a very famous one, Pauli matrices. There are 3 Pauli matrices, but basically you only need 2 because the other one, the Y one, is made from the other 2. So sigma x is the 0, 1, 1, 0. Sigma z is this. And you can see if you take the square of any of Pauli matrices, this is 1, identity matrix, right? So, and also, if you interchange the order of matrix multiplication of 2 different Pauli matrices, you get a minus, okay? And here are the relations. In some sense, that's actually related to the cross product, meaning that if you take the 2 3-dimensional vectors and take the cross product, and you take the same 3-dimensional vector, 2 3-dimensional vector, but you take the cross product in different order, opposite order, you get a negative sign of the result, right? So this one is somewhat similar to that. And actually there is a nice one-to-one correspondence between Pauli matrices and 3-dimensional standard vectors. But we're not gonna go deeper into that because there's nothing more to it, although there's a good way to intuitively understand the Pauli matrices, but we're not really going to use in the quantum computing. And okay, so I said there is a notion called bra, although we mentioned the cat. So if it's the first time being here, the cat is denoted by this, and this is a matrix. This is actually a vector represented by linear combination of 2 cats, cat 0 and cat 1. So I mentioned that cat 0 is corresponds to 2 by 1 matrix. Cat 1 is another 2 by 1 matrix. So if you summarize this, then this general cat, alpha cat 0, beta cat 1, is represented by 2 by 1 matrix. So in other words, as I said, cat is a quantum state of a 1 qubit, right? So it means that you can always represent a quantum state of single qubit as 2 by 1 matrix like this. So again, alpha, beta are complex number, not real number. But what is the bra? Bra is in some sense a conjugate transpose of ket. But in physics, we don't use conjugate transpose. Instead, we use dagger. So, or dual vector. So if you take the dagger on the ket, you get bra. So what is the bra? We'll discuss later, but bra is nothing like, bra is somehow derived from the information of cat, but it's not a cat. It's something that is counter to the cat. So that's why it's called the dual vector. So how do we obtain the bra from the cat? So if your cat is given by this, then the dagger gives you a bra, which is a linear combination of these two bras, bra 0 and bra 1, with a slightly different coefficient. You take the conjugate. So it's actually easy when you consider a matrix representation. Since cat is 2 by 1, bra is 1 by 2, because these matrices are related by conjugate transpose. Okay, so that's the conjugate transpose relation. So cat and bra are related by dagger. That means, and the matrix representation of cat and bra are related by conjugate transpose. So this is something that you have to remember all the time. You can either work with cat and bra only, or you can work with the matrix only. It doesn't matter, but there are pros and cons. Sometimes bra notation or bra and cat notations are easier to understand or deliver the information about the situation. Sometimes matrix are easier when you actually implement the situation in the classical computer. So why do we consider bra? It's because we want to compute or define the notion of inner product between cats. So how do we take the inner product between two cats like this, psi1 and psi1? It's called the bracket. The inner product between two cats are called the bracket. The way we take the inner product is the following. First, you take one cat and take the bra of that cat, bra for psi1, and then you combine it to the cat psi2 this way. So you take the bra 0 coefficient alpha 1 bar and then cat 1 coefficient alpha 2 and then multiply together, and then do the same thing for bra 1 and cat 1. So this is actually same as matrix multiplication, because as I said, you can identify your bra into 1 by 2 matrix and cat as 2 by 1 matrix. What happens when you multiply 1 by 2 and 2 by 1? You get 1 by 1 matrix. But 1 by 1 matrix can be considered as a number, so we can just write it as a number. So that's the same as bracket. Okay? And this is the inner product, because inner product in some sense gives you the length of a vector. The bracket of the same vector, cat psi1, is alpha 1 bar alpha 1 plus alpha 2 bar alpha 2. So that means alpha 1 square plus alpha 2 square. So that's a real number, right? So, and positive real number. So if you take the square of the bracket of the same cat vector, then it's the length of cat vector. So this length in some sense gives you the strength of the quantum state. So what does it mean by strength? Okay, so if the strength is 0, then there is no such quantum state. There's simply non-existence. But if the strength is not 0, actually it doesn't mean anything, because it's there. It's not about how strong your measurement is. It's the measurement outcome that matters. So as long as strength is not 0, the actual size of the strength doesn't matter in the quantum computing. But anyway, in physics, people call it as a strength. Okay, so if you just plug in the values to the bracket definition, you get this relation. So basically, it's a XOR logical operation, right? So if you take, or you can consider it as a Boolean operation. Something like 0 plus 0 is 0, and 1 plus 1 is 2, but 2 is 0 in the Boolean algebra, so it's 0, and so on. And this is quite important. So actually, why quantum computing is quite different, or why quantum computing doesn't, why quantum computing are actually related to the classical computer is that it follows the same Boolean algebra as in the classical computer. So this is why you can actually implement real-life problem that can be modeled into the classical problem into the quantum computing system. So for example, let's compute the bracket of these two ket vectors. So here, I want to take the bra of psi 1. Actually, this 1 should be the inside, not the outside. Because if I put the subscript like outside of a cat, that will imply different information. We'll discuss shortly. So bra of psi 1 is 1 over square root of 2, bra 0, and 1 over square root of bra 1. And then you take the bracket with psi 2, ket. This is minus here. So according to this rule, you only need to pair 0 bra and 0 ket and 1 bra and 1 ket, right? So it's 1 over 2 minus 1 over 2. It's 0. So what does this 0 means? Or like, what is the bracket 1, 0 equals 0 means? I said it's an inner product. Whenever you have two vectors whose inner product is 0, then it means they are perpendicular. So these two vectors, psi 1 and psi 2, they're actually plus vector and minus vector that I mentioned before. They are perpendicular. Okay. So, but be careful, this is not the real vector. This is a complex vector. So you're not looking at the two-dimensional vector in two-dimensional plane. It's a two-dimensional complex plane you're looking at. So even so, it's a two-dimensional vector. Two perpendicular vectors. Okay, so far it's a one qubit system. We only talked about the quantum state of one qubit, right? But now, how about we have more than one qubit? So qubit is just the quantum information stored in whatever that unit is, this quantum material, whatever that information contains in. But you can take the same quantum material, like similar quantum material, in a physically different place and then store some quantum information there. So these two quantum materials, like whatever that is, are physically different objects. But sometimes, we'll discuss this concept later, these two quantum state or quantum information could be entangled each other so that they might interact in some sense. So you must somehow look at all this information contained in this multiple qubit in one system. So that's called a multi-qubit system. So how do we represent a multi-qubit system? So first we'll discuss about the mathematical settings with a tensor product. So suppose we have n qubits and each qubit stores the quantum information represented by ket. So these are psi 0 to psi n minus 1. The reason why I use index starting from 0 is that later these indices will represent the digits of binary numbers. So we're always using index starting from 0. So here, the tensor product of these n ket state is called the n-qubit state. Okay, so what is special about this tensor product? So if there's nothing other than just listing the ket vectors in order, there's no need to use the tensor product. The tensor product satisfies these rules. It's a bilinear rule. So if you take a tensor product of two kets, so each ket represents the quantum state of different quantum object, whatever, the qubit. And if you, for example, say the qubit 0, the zeros qubit, the quantum state is the linear combination or the addition of these two ket states, then you can separate this state into sum of two tensors. So first one is this tensor product and this tensor product. So this is mathematically clear definition, but it's not, if you think about in a real life situation, it's not that clear. Because I said, so if you have qubit 0 and qubit 1 here, so you have qubit 0 represented by the sum of two quantum state, ideal quantum state like 0 and 1, okay? And qubit 2 is purely ket 0. Now, I said these two quantum states are physically separated. They're different states. But somehow you can consider these two things as a one system, and then this one system can be represented as if they are related to each other, so that the quantum state as a whole system can be separated out into sum of two quantum states. One is the quantum state 0 and on the qubit 0 and qubit 1, and then the other is another quantum state in qubit 0 and qubit 1. So yeah, mathematically, if you think about the quantum mechanics mathematically, nothing is weird. It's like almost obvious as linear algebra. But if you start thinking about this as a physical situation or real situation, that's where it gets really weird. So far, I mean, just to finish off these two properties, you can separate on each side of the tensor product, and also you can move around your constant, the scalar, in the scalar replication everywhere around. So you can either put your k outside of the entire tensor product, or you can move your the k to another side of your qubit. They are all the same. So here's another notation for representing multi-qubit system. So this tensor product, it's too much to write every time. So instead of writing this, we're going to combine it into one single string of zeros and 1. And you can consider this as a binary representation of certain number. So we're going to represent as an integer from 0 to 2 to the n minus 1. So the thing is, if you just say, okay, so I have ket 0 and ket 5 representing some n-qubit system, with this notation, you don't know what n is, right? This 5 could be 8 qubits, 5 qubit, ket 5 in the 8 qubit system, or it could be ket 5 in the 100 qubit system, right? So that's why you need to specify number of qubit as a subscript outside the ket. So if you specify all the digits like this, there's no need to specify the number of n, but this is easy, but there is always a restriction. Okay, you can see that the slides are quite long here, so I'm not going to go through all of this today, but um, we'll say something that is necessary until we discuss about this concept. Okay, so as I said, the single qubit state can be represented by 2 by 1 matrix. Multi-qubit can be represented by 2 to the n by 1 matrix. The way we can do this is by tensor product between matrices. So for example, if you want 3-qubit state, all of these qubits have ket 0 state. Then this can be represented by tensor product of 3 2 by 1 matrices. As I said, how do you take the tensor product of 2 matrices? First, if you take the tensor product here, it's 1 times 1 0, 0 times 1 0. And then you take the tensor product with 1 0 again. So it's 1 times 1 0. Now there are 3 zeros below, but no matter what 2 by 1 matrices you multiply, it's all 0. So you get basically 8 by 1 matrix with 1 on top, all 0 on bottom. Same thing for other combination. So if you, so for example, 0 0 1 gives you 1 on the second position here. So you can see how it goes for entire possible choices of 0 and 1. So you either choose 0 or 1 on each qubit. There are 2 to the 3 choices, that's 8. And the matrix that represent this 3-qubit state is 8 by 1 matrix, and there are 8 dimensions. So every time you choose 0 and 1, you get 8 by 1 matrix whose 1 is on certain position, but the rest of the components are all 0. So what do you get? If you have such 8 number of 8 by 1 matrices, that gives you the basis of vector space of 8 by 1 matrices, right? So you can always, well, that's what this means. You can always represent your 8 by 1 matrix as a linear combination of this basis matrix. And where this basis matrix come from? It comes from the basis state. So this comes from base state, such as 0 dot 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 0 ket, something like this. So if your qubits are either ket 0 and ket 1, and if combined into n qubit state, that's the base state. Okay. So any general quantum state on n qubit system is a linear combination of these base state. Okay. Okay. Well. Okay. So how about we do the same thing in the 1 qubit system for the n qubit system? We want to take a bra. We want to say something about counterpart for the n qubit system, n qubit state. It's called a bra. So there's a dot missing here. The way you take the bra is same as taking the bra of 1 qubit state. So simply take the bra on each qubit, but this time, this is the technical reason. You reverse the order of tensor product. So you can see that the index are reversed here, right? So why do we reverse it? Because we want to represent the bra as a matrix too, and we want this matrix representation follows the same rule of conjugate transpose of the matrix of the ket state. And okay, so let's say bra psi, for example, the ket psi is given by this state, which means that it's the 2 to the n by one vector whose elements are alpha 0 to alpha 2 to the n minus 1, then, so this is the number of row and this is number of column. The bra is represented by 1 by 2 to the n size matrix. Okay, and each component is conjugate each other. So you can take this as a definition, but also you can, see why this makes sense, because there are many ways to represent your matrix. First way is to represent it as the big matrix, big 2 to the n by 1 matrix. But also you can think of this as a tensor product of smaller matrices, right? So bra is the same. So you can think about this as a tensor product of bra. So do you get the same number like this one as if you take each bra as a 1 by 2 matrices? Actually, you do. So if you take these matrices of each qubits and then take it into 1 by 2 matrices and then take the tensor product, what you get is you just multiply the size of the columns, which end up being 2 to the n minus 1, and the number of rows are always 1. So you get 1 by 2 to the n minus 1 size matrix, and each components are same as one that you computed in this way. Okay. Okay, so what's a bracket? So as I said, one qubit system has a bracket as an inner product. You also have inner product in n qubit system given by the same bracket. So here comes the reason why another reason why we switch the order of the tensor product when you take the bra. So I want to take the inner product between the ket psi and ket phi here. So I need to take the bra of ket psi. So this becomes this. And I said you have to switch the order of the tensor product. Okay. And then you combine it with the ket phi. So imagine that you put these expression over here. So what do you get? You have some amalgamation between bra and ket in sequel. First, what you encounter is ket phi n minus 1, right? So you combine these two to make bracket. So this bracket is the bracket on the n minus first qubit. Okay, and then this becomes the number, just the constant or scalar. So you can take out this constant outside of the tensor product. And then what you encounter is the n minus second bra and ket. You combine into bracket, take it out as a constant until you end up getting bracket on the qubit 0. So that's how you define a bracket on n qubit system. So I just want to ask, is it too abstract or is it too obvious? Does anyone want to see the example? Yes. Oh, you want to see some example? Let's see. I forgot to put some examples here. Maybe it's about the unitary. Okay, so how about, okay, so it's all right. So let's start with a 2-qubit system. Okay, so how about right plus as of the form okay. So how about this one first? And then let's see. This is our first first cat in the 2-qubit system. And this is another cat. And compute the bracket of this 2-qubit system. Okay, so I think it's a good time for the discussion. So think about these two questions and whether or not you get answer, try to talk to your friends next to you and then discuss in the group. We'll talk about this in the class after about 5 minutes. That I thought everyone knew, but this is this and this is. Okay. First, any group? Is there any group wants to explain first? Uh, so I don't want. I mean, I'm not asking the actual answers. I'm asking for how you got your group derived or thought about the questions. So, any group want to talk first? So how about group 7? Is there a group 7? No, group 6. How about group 6? Yes. So you're the first person in the Kim Sung-woo? Who's Kim Sung-woo? Not here? Okay. Yoon Myung-jin? Okay, so how did your group okay, so here's the question, sorry. This is the question. So how did your group thought about the first question? What's your approach? You transferred the CAD notation to matrix representation? Okay. Okay. Mm-hmm. Did you use metrics for the second question? Did you use the matrix representation for the second question too? Okay. So any group worked without matrix representation? Is there any group worked without matrix representation? Okay. So everyone worked with you did? You did not use the matrix representation? Okay. So how did you compute the first one? Did you use the tensor product property? Okay, so multilinear property of tensor product. Okay. And all right. So how about the second one? You also not use the matrix representation? Did you use the matrix representation or just work with the bra? Did you work with the bra? Uh-huh. Okay. Yeah, you can use the property of tensor product, but well, so here the question is, and on the second question, you can take the bracket of n qubit system, right? But the given state, given n qubit n qubit state, is not given as a single tensor product. It's a linear combination of multiple tensor product, right? So I just want to know, how did you compute this bracket? Anyone? So everyone worked with the matrix. Okay. All right. So so it's, the main goal, the first goal of our first half of the semester is making a simulation. So that simulation means that you need to implement an imaginary quantum computer in your classical computer using the program, and there should be some way you store the information of the quantum state, right? So matrix is one way you can make it into a data. And the other way is, well, maybe you can work with this cat symbol, right? So if you're using the cat symbol and trying to take the inner product, there's always also has to be a rule that allows you to compute. So let's try to do this without matrix multiplication. So I want to take the bra and bra of 0, bra of 0, tensor product, bra 1, and bra 1. So when I take the inner product of these two, so as you can imagine, I mean, if you remember what you learned in the linear algebra, the inner product is also bilinear. That means whenever you have a linear combination on one component of the inner product, you can split it into the same linear combination, right? So I'm going to write down everything here. 0, 0, plus 1, 1. So it's this psi bra inner product, so with the phi, the phi bra, and the psi, which is plus, minus, plus 0, 1. So you can distribute your bracket throughout this parenthesis. So first this one, this two, and this one, and this. So the first bracket you get is 0 bra, 0 bra, bracket with plus, minus. So how do you compute? You compute this way, right? It's already, the order of the bracket, the bra is also already switched, right? So you take the 0 bracket with plus and 0 bracket with minus. So how do you, what is the 0 bracket plus? So 1 over square root of 2, right? So you can also do the same thing for this. So we have 0 bra inner product with plus, which is a linear combination of 0 cat and 1 cat like this. And then you take the 0 bra inner product with 1 over square root of 2, 0 cat minus 1 over square root of 2, 1 cat, and so on. So there are 3 more brackets to compute, but I'm not writing everything here. So you can also distribute the bracket here and bracket here, right? So you get 1 over square root of 2, 0. So 1 over square root of 2. And here you also get 1 over square root of 2 plus 0. So the first bracket is 1 over 2. And you can do the similar for the 3 other brackets, right? Okay. So I think the first question is not that hard. So the reason why I want you to discuss is not just checking whether you got the correct answer, but I just want you to, explain or just see how you understood well, and also listen to other people how they understood the same material. So we'll see other topics, and then I'll come up with other examples. So far we talked about the bracket of the n-qubit system. And this is how you take the n-qubit system. So this is just the general notation for general state, and nothing special about this expression. Now here comes the interesting part. So before I go through this slide, we just took the bracket, right? First, we start from the cat, and then we take the bra, and you combine bra and cat to make a bracket, which is the inner product. Now, I think in this, so physicists developed this notation, and what physicists are good at is imagination. So they thought, what if they take cat bra instead of bracket? So just to change the order of the layout, instead of putting bra in front, what if you take the cat in front of bra? What would that represent? That represents a linear transformation. So the mathematical definition of a linear transformation is this. You have two vector spaces, and you have a mapping between elements in two vector spaces. And the mapping is not random. It satisfies this rule. Whenever you take the linear combination in the domain space, like alpha u plus beta v, the result is also a linear combination of the same coefficient, alpha tu plus beta tv. So in some sense, if you think about this in the situation of two-dimensional plane, it means that you just take the line into line. So that's why it's linear. So you don't take the quadratic or cubic. It just goes line, line. Now, actually what happens is whenever you take the n-qubit system or the qubit states of the n-qubit system, you collect all of these into a set called Hn. It's called the Hilbert space. Hilbert space is, in mathematical settings, it's the vector space plus inner product. So it's not just a vector space. You need inner product in order to call this vector space as a Hilbert space. So what's the inner product in our setting of n-qubit system? It's the bracket. So that's why we call this set of all qubit states of n-qubit system as a Hilbert space. So now what's the relationship between linear transformation and the Hilbert space? Whenever you want to take a linear combination, so basically the Hilbert space is a vector space, so you can imagine a linear transformation from Hilbert space to a Hilbert space. So in reality, you cannot get rid of qubit from the n-qubit system. So you always have to take the n-qubit system to another n-qubit system. Your qubits are not changed. Okay, so whenever you want to talk about linear transformation between Hilbert spaces, you're talking about the same dimensional Hilbert space. That Hilbert space actually represents the same qubit system, although. So here, U is a linear transformation, and such linear transformation is called quantum operator. It's called quantum operator. So it actually changes the state of n-qubit state. So how do you represent quantum operator? That's where cat bra appears. So imagine you have two cats, psi1 and psi2, and you take the bra of psi1, and instead of bracket, you take the cat bra, like this one. So this is cat and this is bra, right? And whenever you have this cat bra, you can consider this as something that acts on another cat, like psi cat. So it's again, so this is something that we call cat bra, and when we combine this cat bra with the cat, we call it acting. We call it this thing acts on the cat phi. So what's the result of this action? So you can combine this bra and cat and makes a constant, like bracket constant. And then this constant is the constant that multiply on the remaining cat, which is psi2. So as a result, what we get? We have something called cat bra, and it acts on the cat, which represents n-qubit system, and actually gives another cat, which represents another n-qubit system. So it actually gives the map between n-qubit system to another n-qubit system. And it happens to be the linear transformation because of the properties of the bras and of the bracket. Therefore, this cat bra gives you quantum operator. So how do you represent the quantum operator on 1 qubit? Okay. Oh, by the way, this is 1 qubit. Sorry, if I thought it was n qubit. So it's a 1 qubit. Okay. So how do you express the general quantum operator? So it's either it's either sending 0 to 0 or 1 to 1 or 1 to 0 or 0 to 1. So think about this cat bra 0 0. So it sends 0 cat to 0 cat. How about 1 cat? So if you take the bracket of bra 0 and cat 1, it's 0, right? So it's a 0 times 0 cat, that means 0. So as I said, not all quantum states are either 0 or 1. It could be 0. All the coefficients of 0 and 1 could be 0. That means there's no such quantum state, 0, right? So it kind of annihilates the quantum state 1, cat 1. So anyway, this is also perfectly fine quantum operator. It just preserves the cat 0 state, but annihilates the quantum state cat 1. So this is that quantum operator. And you can imagine what this does, and that does, and so on. So this is all possible quantum operator that you can think of. In every quantum operator is a linear combination of these 4 quantum operators. So we call this quantum operator also as base operator. And the nice thing about the cat bra notation as an operator is that you can also represent them as a matrix. And think about how you represent the cat bra like 0 0. So bra 0, I said it's 1 0 2 by 1 matrix, and cat 0 is 1 0, and bra 0 is 1 0 1 by 2 matrix. You can multiply these two matrices, right? Although it's the rank 1 matrix, it's a 2 by 2 matrix of rank 1. You can still make a multiplication. So it's a 1 0 0 0, like 2 by 2 matrix like this. So once you have a 2 by 2 matrix, you can multiply it onto 2 by 1 matrix to get 2 by 1 matrix. So for example, if you have 1 0 0 0 multiplied on 1 0, you get 1 0, and you get 1 0 0 0 multiplied on 0 1 to get 0 0. So 1 0 represents the cat 0, and 0 0 represents 0 vector, 0's quantum state, right? So that matches well with this computation we already did. The same thing for other base operators. Okay. So if you combine all of these and as a matrix, then you can also represent your quantum operator on 1 qubit as 2 by 2 matrix like this. So sorry for a little bit, cut it here. So in summary, every quantum operator on 1 qubit system can be represented as 2 by 2 complex matrix. Okay. So here's an example. So let's try to discuss the action of the operator cat bra, like this one, plus and 0, on the 1 qubit system. Well, let's do it together. So you can do in 2 different ways. One is you can make a matrix representation of this cat bra, and then try to understand the linear operation of the linear transformation. Or you can simply just throw in cat 0 and cat 1 and see what happens after you throw in them. So let's look at the matrix representation first. So first one is cat plus, so it's 1 over square root of 2. And second is 0 cat, 0 bra, so 1, 0. So this is 1 over square root of 2, 1 over square root of 2, 0, 0. And that acts on 1, 0 and sent to 1 over square root of 2, 0. And also one sends 0, 1 to 0, 0, right? So what does it do? So this operator sends cat 0 to cat 0, but different scale with the coefficient 1 over square root of 2. And it sends cat 1 and annihilates that. It sends to 0 vector. But you can also do the same computation with cat notation. So what if I take cat 0 and put it into the operator? So 0 bra, 0 cat combined together to make, oh, wait, what happens? Sorry, so I made a mistake here. So this is 1 over square root of 2. Yeah. So this is actually not cat 0, sorry. So this is plus 1, plus cat, right? So if I just use the cat notation here, so if I take the bracket of 0 and 0, I get 1, right? So what I left with is plus cat here. And what if I put the cat 1, then 0 bra and cat 1 combined together to get 0. So it's a 0. So either way works fine. Okay, so what's good about this operator? Now, we'll talk about later about how quantum gates are operating on each qubit, but this quantum operator acts as a quantum gate later on. And acting on quantum operator on each qubit can be done independently. So again, think about the quantum n-qubit state, quantum n-qubit state, and each qubit stored in each physically different qubit material, quantum materials are just works independently. They're just the different materials. So you can apply quantum operator or quantum gate on this qubit or that qubit, this qubit. Acting quantum operator on qubit 0 doesn't affect anything on the quantum qubit 1. So this is all can be done independently. So this process of applying quantum operator can be described as a tensor product. So for example, consider this U and V are quantum operator on one qubit. So if you take the tensor product of these two, that means you're applying U on the qubit 0 and V on the qubit 1. So qubit 0 and qubit 1 is just a name to distinguish two qubits. And this acts independently. So U goes to the first qubit and V goes to the second qubit. Okay? So you can imagine these two qubits are just one qubit system, or you can consider this as a separate system. So each system also consists of several objects, several qubits. So this U can be an operator acting on the n qubit, so it goes to the n qubit system state, and V goes to the m qubit system. And the result is the tensor product of new quantum state representing the n qubit system and m qubit system independently. So everything is independent. Okay. Okay, so I think the order is a little bit mixed. So whenever you want to express n-qubit quantum operator, then you can express it as a tensor product of one qubit operators, like this. Right, so how about we, maybe, is there more? Yeah, how about we give some example at this moment? I think it's a good time to give some example. So here, I'm gonna make, sorry. the same operators. Sorry. Like this one. So let's think about this operator. So it's a 2-qubit operator. Explain the action of this 2-qubit operator. What I mean by action is there are qubits in 2-qubit state, like 0, 0, 0, 1, 1, 0, and 1, 1, right? So these are all base states of 2-qubit system, all 4. Now, if you know what these base states are sent to by this action of operator, 2-qubit operator, then you can fully determine any qubit states are sent to any other qubit state. So what I mean by explain the action of this operator is find out the question marks here. Try to compute this. Plug in 0, 0 here. What happens? Remember that you can work as a bracket or as a matrix. The bracket, in this case, bracket is easier to work with, but you can also start try to see whether the matrix representation is the same way. Left hand side, you get operator represented by 2x2 matrix. Here, you get the 2x2 matrix. What happens when we tensor plot a 2x2 matrix? You get 4x4 matrix. What you want to see is how this 4x4 matrix on 4x1 matrices. 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0. The basis of the 4x1 matrix. 4-dimensional. Okay, so shall we do together? I think it's not that hard, so I want you to call out the answers here. So where does this tensor 0 go with the action of this operator? Plus tensor 0, yes. Why? So this operator, the 1-qubit operator, acts on this one. Okay, so 0, 0, yes, that's bracket 1. So you get plus cat survived. So in the second operator acts on this one. Now there are two operators added together. So first operator acts on here to get cat 0, and second operator has 1, 1. So now bracket 1, 0 is 0, so it kills this cat 0. So basically this is the result. And you can do the same thing here. So that's how you basically do it with the bracket operator, bracket notation. Now, as I said, you can also use the matrix representation. So this one is, what was it? I forgot. 1 over square root of 2, 1 over square root of 2, 0, 0. And this one is 1, 1. Right? So you can use the matrix application of each 1-qubit operator and then take the tensor product to get now big 4x4 matrix. So 1 over square root of 2, 0, 1 over square root of 2, 1 over square root of 2, 0, 1 over square root of 2. So these are all 0 here because there are 0 here, right? Now, does it make sense to you? Let's compare the first column. So when I multiply to this matrix on the right by 1, 0, 0, 0, I get the first column, right? So first column means it's a cat. It's a quantum state of 2-qubit state, 2-qubit system, with 1 over 2, the coefficient on 1, 0, 0, 0 and 0, 0, 1, 0. So 1, 0, 0, 0 means 0 tensor 0. 0, 0, 1, 0 means 1 tensor 0, right? So it's a linear combination of these two cat states with the constant coefficient 1 over square root of 2. That's actually same as this one, right? So everything is mathematics. The reason why I'm showing you all the mathematics first is that once we get to the concept of entanglement and whatever the EPR paradox, the quantum paradox is, you get confused if you don't comfortable with the mathematical settings of the quantum computing, because everything works as a math formula. If you really want to work with work in a quantum computing without any confusion. So if you start to thinking about in a physics sense, then there's a famous saying that quantum mechanics or quantum theory doesn't make sense at all. But it makes perfect sense when you think anything quantum mechanics or quantum computing in this mathematical settings. Nothing, weird about anything. So, yeah, we'll talk more about the multiple qubit system next time. And also, I'm going to upload this note and also probably upload the next slide on the chapter 2. So if you have any questions, let me know. And also, if you need any other information, if you're first time here, if you want to ask about the class, let me know after class. See you on Friday.